Okay, Assalamualaikum and good morning to everyone. Today we are continuing our lecture on chapter 7, which is signal conditioning, data acquisition system, and interfacing. So, can anyone verify that you can listen to my voice? All right, thank you very much. So, for the past 2 weeks, you have seen the application of data acquisition, signal conditioning, and interfacing from our lab sessions. So we were using LDR sensor, which convert light intensity or light irradiance into um, electrical current. But before, so basically, last week we were using light dependent resistor LDR sensor. So that LDR basically converts light intensity into proportional resistance. But basically, the relationship is inverse proportional. So inverse meaning that when the light intensity go up and then the resistance go down. And actually, to convert the light into voltage, we had a signal conditioning, which is using a voltage divider. Can look back at the lab sheet. We get analog, analog uh, signal sent into the Arduino. uh, the Arduino uh, analog pin. So that is actually some conversion, data conversion from analog to digital. Okay, basically analog to digital converter. And we have seen an interface between the Arduino and LabVIEW. And basically the interface was using USB. Uh, so today we will look into some other type of signal conditioning and also interface which are applied in the industry. So this is basically what we're going to see uh, in this chapter. So basically, we're going to see first the type of signals. You need to understand the signal parameters, okay, signal type of signal, and also type of data. Then we're going to see signal conditioning, how to basically improve the signal that we have, we are converting. You want to convert. So there are some methods will involve like amplification, filtering, and analog digital conversion. Basically, one whole chapter we have covered before. Then we're going to see some other, type of data acquisition system. especially the type of data acquisition system, or, or that is common in the industry, and how this data acquisition system differentiate with each other. So, and then basically interface system, you have seen LabVIEW. One of the examples is basically a graphical user interface, and there are other user interface that can be developed uh, as an interfacing system for your system, your data acquisition system especially. Now, let's see uh, the flow. This basically you can recall back some of the other examples that we have carried out even in the uh, first lab till the second lab. So the our physical system of physical system that represent the physical parameters like this irradiance, like our uh, ambient temperature, humidity. Okay, so the signal basically vary over the time for um, in in a very smooth manner. For instance, you can see. So if you notice, okay, our day in and day out, okay, the sun trajectory, okay, go up and go down. So we take the um, ideal day where there is no sun. Sorry, there is no cloud. Okay, means that the sun is shining uh, basically 8 hours. So you can see the light intensity, okay, max at the noon. Where, so you can see that in the physical system, the signal may vary continuously. Then when we convert, okay, the physical parameter using sensors, so the signal that coming out may not be as smooth as the response may not be as smooth as the physical parameters. So the signal may contain uh, may be uh, enveloped with noise, and this noise may be introduced by the many factors. For instance, even the noise coming from internal system or from the sensor itself. So to smooth out the noisy signal, we can do some process, what you call as signal conditioning, which filtering the amount of unwanted noise. So this noise basically exists at certain frequency. So frequency, let's say our original signal, let's say 50 hertz. So it may be enveloped, okay, by noise, okay, noise, and the noise may be more than 50 hertz, may at 1 kilohertz and above. So we can filter it out using filtering circuit, for instance. Then we know that our digital system, cannot communicate or cannot process analog signal. Therefore, we need to convert the signal into digital, and the signal digitized into uh, digital representation, and then that goes into our computer, and then our computer can process or transfer the data into the other. Um, for instance, if you remember how the LabVIEW fetch the data from the Arduino, and that data is actually um, character character, even though um, we see that the number in decimal, but actually represented in characters. So that character can be converted, back into float or the decimal values using some functioning block in the LabVIEW. So there are some okay um, the mapping of physical phenomena of, or you can say physical variables that can be converted into by sensors. For example, temperature. It can be converted into electrical signals either directly or indirectly. For example, thermocouple can directly convert into voltage or EMF, but resistive temperature device or need is a passive sensor, need some external power supply, and same as thermistor. And most of these we have covered in the previous chapters, and including light, okay, photo sensors like LDR. This we have covered in our lab. So this is just repeating what we have covered before. So analog signals basically signal that varies continuously with time, like sine wave. That's the best representation. But digital signal is discrete voltage level, okay, or current, actually comprised of discrete current states. So digital signals try to mimic the actual analog signal, but the conversion happen at a discrete step. Okay, it cannot happen at uh, at any time of the time. So it only happen at a certain discrete steps. Okay, these are like for instance, okay, analog may vary continuously, indefinitely, will continuously uh, change. But for digital, we can set a voltage threshold. So, for example, in this case, when we one set that any signal that below 25 or 21.87 millivolts, so we assume that as zero. But when the signal pass 21.87 millivolt, that is one. But this conversion uh, may not happen at just one threshold value. So it may, there's a method that we can set the limit, the low and high limit, where the signal, if does not uh, or reduce below the minimum value, so the signal, for example, will retain at one. Right. So pattern basically uh, define the profile of the signal over the time. Um, so this signal and shape is important if you do some signal study or signal characterizing. For example, okay, if you uh, to identify in a EKG human uh, vital signal of the body. So the pulse looks like a triangular. So then you can study the pulse uh, time constants, like the time constant between the peak and the valley, or the maximum to the minimum. Then for digital, usually we going to find the information in bit patterns, what's called as bit pattern. Usually we don't go for the shape or the character shape characteristic, but for digital, we usually look at the pattern bit pattern. For example, in this example, we set a boundary, and between that boundary, we identify the 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 binary digital or the binary values we can capture between that between that border or that we set. Like for example, in this case, a 00110 is the bit pattern or bit value that we captured between the space that we want to identify. Frequency for analog, usually analog, in term of the frequency measure in hertz, which is can represent the how how fast the signal complete one cycle. And for digital, usually we call it as the rate. Okay, uh, how fast the digital bit is transferred in, or how many bit of digital signals transferred in 1 second. For example, so that's the difference between analog and digital uh, frequency and rate. So we're going to see more of the how the signal is processed. Um, for example, okay, we know that we want to measure signal, or we want to measure signal using temperature. So in a conventional way, we can measure the temperature using thermometer, where we can, for example, use um, thermometer made of especially liquid put inside a bulb or glass casing. So uh, basically the liquid will expand when the temperature increase. So we can put a we can put a range where the level of the liquid will increase. So that is done by visually. So, but in digital is we have to manipulate, or we have to do something so that our system can understand what is happening. Uh, so let's see it on the side of the signal conditioning. So there are many uh, basically there are many method or type of signal conditioning, and this uh, serve a certain purpose. For example, uh, amplification. So amplification is one of the common uh, signal conditioning purpose, where we need to increase the level of signal of our output, meaning that the output from our sensor. Then we need uh, a circuit or a way how to amplify that signal. And then also like filtering. So this is basically filtering. So we're going to see how it can be carried out. So you can see the purpose or the function of signal conditioning method list out here. But I'm more interested in showing you some example, okay, using the circuit. Right. So the first important or the common type of signal conditioning is called as amplifier. So the purpose of our signal condition of amplification is to increase the input signal amplitude. So this is very useful for signal that uh, the output of our sensor, for instance, is very low, let's say in microvolt or millivolt. For example, the output of thermocouple, output of thermocouple usually low and need some amplification. So the amplification usually done by using this common device called as the op amp or operational amplifier. So the op amp basically can retain the fundamental characteristic of our input, but in the same time increase the level. And also the amplification can be done without any phase difference, for example. Like for example, the if we have a pressure sensor, okay, the output is between 0 to 10 millivolt, and the signal need the amplification of range between 0 to 5. So let's say the input level is 0 to 10 millivolt, but the output we need it to be 0 to 5 volt, which means that the amplification gain needs to be around 500. Okay, the gain. So how do we get this gain? So gain is equal to output, basically equals to output amplitude divided by input amplitude. So let's say that in this case the output is 5 volt and then the input or the maximum input is 10 millivolt, so that we get 500 the gain that is required to amplify. Okay, some characteristic of the op-amp. The op-amp has high impedance input, high impedance input and low impedance output. So what it means by high impedance output means that I is plus is 0 ampere, and also Z or the impedance, the input impedance will equal to infinity ohm. We'll see that in some examples. All right. So these are the type of amplification. It's called as non-inverting amplification. Non-inverting amplification, whereas V out is equal 1 plus R0 over R1 V in. So this is non-inverting, and this is called as inverting, whereas the output will be inverse. But inverse of the input, but multiply with the gain. Okay, the gain acquired from R2 over R1. Now, this one is called as voltage follower. So voltage follower is important to in the case of where you want to connect with output, okay, output with low impedance. Okay, so if your output, let's say this is useful for connecting, let's say in this case V in with low impedance output or load. So because let's say this output is connected to a motor, so the current that drain into the motor, okay, is not from V in. Okay, if we directly connect V in to the motor, so V in may not be, the current supplied by V in may not be enough to run the motor, because motor have low impedance output. So voltage follower is best for that application. Okay, hang on. So we have this, for example, non-inverting amplifier. So how let's so in this example, we have our V input here. So V input here is going to the V1 of the op amp. So then don't get confused with this this arrow. So just ignore that arrow. Okay. So we can redraw that signal or simplify it like this. So this is our V in. So this is our V out. And this RL will not involve in our calculation. Okay, so so how does it? How do we derive V in? So basically, we want to get V out equal to something V in. So we need to find what is the equation, right? So there are some fundamental things that you need to know about op amp. So which is number one is I minus and OI plus. So I minus, or the current that go into the negative port, or the current that go to the positive port, I minus OI plus will be equivalent to 0 M. Okay. Why? Because op amp has a high input impedance, very high input impedance. Okay, high input impedance. So no current going to the negative input, or to the negative or to the negative or to the positive input. I plus equal to I minus equal to 0 ampere. Then the second thing is that the potential here V negative, and then the potential here V positive. So V plus minus V negative equal to 0 volt. So this is first relationship. So this is the second relationship. Okay. So in this case, we know that V plus is equal to V in. Therefore, so this is number 3. So 3 into 2 V in minus V minus equal to 0. We get V in equal to V minus. Okay. So ini relationship number 4. Okay. So next, we apply KCL here on the negative input. So we can assume this is as I1, and this is, we can assume as you can say as I2, and this is as I minus. Okay, so we know that if we apply current Kirchhoff law here at this node, KCL, so we know that I1 equals to I minus plus I2. So the amount of current that flow into the node is equivalent to 0. Or you can say the amount of current come in equal to the current that come out. So I1 equal to I1s plus I2. So then next you can use Ohm's law. So for I1 is zero potential minus B minus divided by R1 equal to I minus here is since I minus is 0, so I minus is 0 plus I2 is from this node. Okay, the potential difference of this node to this node for I2. So it means that V minus okay, this is our V out divided by RF. So next we get so no we know that V minus equal to V in. So minus V in over R1 equals to V in minus V out over RF. Right? Then V in minus V out equals to negative V in over RF R1 or V out minus V in equals to V in RF plus R1 and finally V out equal to V in RF over R1 plus V in or V out equals to V in 1 plus RF over R1. So this is non-inverting op-amp. So you can use the same process to find the relationship of V out to V input for this example. So in this example is proof that V out is equivalent to V in but multiply with negative RF over R1, which is the output is inverse. So in other case or other example, we can use the op-amp as comparator. We can set the op-amp to compare two inputs. Like for example, in this case, V1 and V2. So the limit or the saturation is basically the what is the VCC or V plus. In this case, V plus is 10 volt and V negative is negative 10 volt. So in any case of if V1 is more than V2, so it saturates F at V negative or VCC negative or negative 10 volts. If in other case when V2 is more than V1, so saturate at V plus or 10 volts. I'm going to go here. Right. So in this case, op amp is used as a comparator to measure temperature, where the compare this example where this V plus and this is V negative, and this is our input, negative, and then this is our input. So this V negative is set as V plus multiply with R over R plus R, or V plus over 2, our V negative threshold or input value is V plus over 2. But for the V negative, sorry, V negative is set at V plus over 2. But for V positive here, V positive is equals to V plus multiplied with the thermistor, our thermistor R1 over R1 plus R2. Means that if the thermistor here, maybe, okay, the characteristic is if the temperature increase, okay, so the resistance go down. Okay, means that the resistance is inversely proportional to the temperature. So we can take that like this example, when if any case that V2 is more than V1, then we'll saturate at positive. If V1 or otherwise it's saturate at negative. So in any case that the temperature is reduced, and this is used to measure temperature. If the temperature is reduced, okay, temperature is reduced means that resistance increase, or thermistor resistance increase. So V plus will increase. So in that case, when V plus increase, so V plus will be more than V negative. So this output will be high. V out will be high, and then basically open the gate of this transistor or VBE, will allow current to flow, and then will close this relay. Current will go or flow from V plus to the positive through the collector and emitter of the transistor. But in the case of if the temperature increase, so resistance will reduce. So then V plus will be less than V minus. So the gate or the transistor gate, VB will not be more than 0.7, so no current will flow through the collector and emitter of the transistor, so the relay will be de-energized or open circuit. These are other op amp like summing, differential, integrating. Okay, you can use the same. Okay, I have assist you how to derive the circuit in this part, so you can repeat the process to find the output of the circuit relationship with the input. So in this case, the output is the sum of the input, but multiply with the gain of RF over R. And also another thing is that the output is inverse, or 180 difference. We'll not go to this. Uh, not go to this. We will go to directly to this filtering part. So filtering is a process where you want to remove the unwanted signals and only allow the signals that is important or useful for your system. So in this case, okay, where you want to remove or to block out any noise coming out from the system, okay, by using the filtering method. So there are type of or a character of ideal filter, either low pass. Low pass means that you only allow signal at the low frequency. So this graph can show you the frequency of the range of the bandwidth of the frequency, and then the signal that is transmitted. So for low pass, basically only allow frequency below your what is called as the cut-off frequency. Okay, this is the cut-off frequency, cut-off. So for low pass, you only allow the signal that lower than the cut-off frequency. Anything higher than the cut-off is removed. Whereas for the high pass, okay, you only allow signals that is higher than the cutoff. Okay, so this is the signal that is allowed, and this is supposed to be no signal or no response at this range. Okay, this is forbidden gap or forbidden or filtered area. So there should be no gain or no signal transmitted in this area. So similar as for the low pass. And this is band pass. Band pass means that you set the low cutoff and high cutoff, low cutoff and high cutoff. So you only allow the signal in between the low cutoff and the high cutoff, or you only interested in that range. Of course, okay, the filtering cannot happen ideally like that. So the reduction will have some, okay, take some response or to take some reduction. And for the band stop, basically inverse of the band pass, where band stop basically you don't want the signal in between the low and high cutoff, but the rest, okay, you accept. So basically, band stop is the combination of low pass and high pass. Okay, this is so D is actually A combined with B. Okay, D, actually. Right. So this is another type of conditioning, which is increasing the sensitivity of sensors or transducer. And in this case, we are using Western bridge. So we have done this in our first lab, where we have a Western bridge, and you try to change the sensitivity, right? The output, and then you measure the output based on your modification of the one of the arm to achieve balanced state. But in this case, so the uh, gauge output itself is not directly voltage. So we can use a simple voltage divider, but the sensitivity will not that significant. So for this case, we use we connect the transduce the sensors or the transducer, okay, into a Western bridge. And then of course in Western bridge we need a power supply and two fixed, in this case two fixed resistor and two transducer, okay, each in on 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 its own arm. Uh, so this will significantly increase the sensitivity of the output, where the output is measured in the middle of the bridge, as can shown in this example, where V measure is the total or the final output of this configuration. So V measure will be, in this case V measure will be in proportional to the RG2 and also RG1, but the sensitivity will be at higher or at higher scale. Okay, so and then signal conditioning bridge DC AC, we have covered that in chapter 2. So that is actually signal conditioning. Voltage divider is a common one. Remember that is in our as class examples. Sorry, in our experiment where we use LDR. LDR. Sorry, the LDR is at the bottom, right? But we have a pull-up resistor, right? So in our last example, we use LDR. R pull, which is 10 kilo ohm, and then our LDR, and then we have our output. V out to V. Let's see, this is V in. V in multiply with R LDR over R LDR plus R pull. Right. Okay, so the next thing or the opposite function of amplification, we have what it is called as attenuator. So attenuator basically decrease the input signal amplitude, or we decrease the gain, decrease the gain. So means that in this application, gain for attenuator gain must be less than 1. Okay. So it is very useful for as example where you remember that in any conversion ADC to our ADC, remember our ADC analog to digital converter. Um, so our ADC conversion of analog to digital. So we have our V in. So V in is equal to N. Sorry, V ref multiply with N over 2 to the power of N. So V ref. So our conversion of analog to digital converter, the conversion must not be exceeding the V reference value. So if the input is more than reference value, so there will be no meaningful conversion from the analog to digital converter. So that's why a attenuator circuit is important. And then again, the most common attenuation circuit that we can do is called the most famous one is called as the voltage divider. Okay. So for in this case, the voltage divider so the VD is the Vs multiply with R1 over R1 plus R2 is the order. VD is in the function of is equal to Vs but multiply with R1 over R1 plus R2. So this is basically attenuation of the um, of the Vs. Okay, so Vd is actually the attenuation of Vs. So I do want to go to this because we have done this in our the derivation. We have done it in our previous class where if we have wisdom bridge, then we assume that if the bridge is in balance, so if the imbalance we get the output is equals to the VD minus VB, then you can derive that uh, sorry. Okay, let's see this example. A platinum resistant temperature has a resistance of 100 ohm at 0 degree Celsius is placed in one arm of wisdom bridge in each of the other arm also being 100 ohm. Okay. If the resistance coefficient of the platinum is 0.00 K, find the output voltage from the bridge per degree in temperature if the load cross to be if okay the load okay. So this is basically simple. Okay, but where you have a supply 6 volt and you have wisdom bridge, and then one of the arm is connected to a R platinum resistant temperature RTD. Okay, so one is connected to RTD. And then this is your V out. V out. So this, let's say this is R, 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 because R 100 here, we can assume this R as 100 and this is RTD. But it doesn't state which. I'm going to put the RTD on this side. I'm going to put the RTD here. Okay. So let's say this is VA and then this is VB. So there is a point here. If the load across the output can be assumed to be infinite, means that V out here, the current here will always be 0. Okay, so if this statement is there, means that the equation VA minus VB V out is equivalent to VA minus VB will always be true, which is V out is VA is RTD divided by RTD plus R multiply with, or we can say multiply with 6 minus VB VB here, which is R over R plus R multiplied with 6, right? So actually here, when you know that 6, so you get V out equivalent to RTD minus R over R plus R. But in this case, oh yeah, this is true, still true. And also if you can use this equation, also true, no problem. Either you can use this equation or this equation, because this equation here assume that delta R is small. But anyway, so if we can use this equation, no problem, same. So we calculate the change of the RTD using this equation. So the change is about 0.39 multiplied with 100. Oh, sorry, yeah. So the RTD is 0.39 K. So, and then we can similarly get the answer from V out equivalent to 0.39 multiplied with 6 over 0.39 K plus 100 minus, this is R plus R, is that 1 over 2, 1 over 2, R over 2R, 6. So V out equivalent to 0.39 K multiplied with 6 divide by 0.39 K plus 100 minus 3. So since you can get the answer, right? Now we go to this example. What is this example? A type T thermocouple as the characteristic shown in is for signifying the thermo rotor circuit and the value, the maximum temperature saturated information as number 2, using information from 1, 2, and 3, plot the graph output from signal conditioning versus temperature for the range of 0 degrees Celsius to 400 degrees Celsius. Also find the sensitivity of your signal conditioning. Alright. So there are 3 as the characteristic shown in figure 1, an op-amp with saturated voltage is used for signal conditioning. Find the thermoelectric voltage for 0 degree, 50 degree, and 100 degrees Celsius. Draw the circuit and their value for signal conditioning to produce voltage for 5 volt output at temperature 100 degrees Celsius. So means that we need to do some amplification. Okay. But before that, okay, the question asks you to find the thermo output, number 2, the EMF for 0, so this is the table I have taught you how to find the EMF from the table, especially when the, let's say, the value is in between, okay, the line or in between the, it's not available directly from the question. But I'm going to assume that this thermocouple reference junction is equivalent to 0 degrees Celsius. So find the voltage at 0 degrees Celsius. So this is start from here 0. Okay, go here, and then we 0 plus 0. So this is, okay, 0 volt. Next, 55, 0, 50 here, and 55, 50 plus 5. So we go here, okay, and this is 5. We will cross this value. That will be 2.251, and this is all in millivolts. Okay, millivolt. Don't forget, this is table is in millivolt. And then what is the output at 110? Okay, 100. Can go here, 100 and here, or this 110 here, and 0 here. You put here 0, you get the answer 4.750 millivolt. Right. So draw the suitable circuit and their value for signal conditioning to produce output 5 volt. So means, okay, your thermocouple, you remember your thermocouple is 2 thermocouple. Two dissimilar wire that made into, okay, let's use different two similar wire made into two junction. So this is T ref. This is 0 is SS. And this is T measure. So this is connected to a circuit. So the most, the doesn't ask you to to find the answer or to find the suitable value or the value. Okay, suitable circuit and the value. Okay, so means that we need to do some amplification. The amplification to get 5 volt, 5 volt. So and then another thing is that the amplification must be non-inverting. Okay, non-inverting. So the most suitable one we can use is this non-inverting amplifier, which is this one. Okay, look like this, but the input, okay, go. Sorry, like this one. Okay, so that's your junction here. Okay, thermocouple junction, and this is the non-inverting. So we need to do some a bit modification, okay, on the connection. So this is a coil junction, hard junction. Let's snip this part. Right. So circuit will be look like this. This is, okay. So the circuit will basically look like this. So we'll stop from we will stop here and just some announcement that we not going. All right. So so we come back. Okay. Again, I repeat for the last about 10 minutes. I repeat. Sorry. So we have come to this example. Okay, last week example where the example of a thermocouple, and this thermocouple basically require um, the signal conditioning circuit. So thermocouple, as we know, is two dissimilar wire, till two dissimilar wire combined together to create junction. Two junction, one for measurement and second for the reference, and then the output at the terminal V plus V and V the potential, okay, V plus minus V minus, means plus minus, or the EMF is proportional to the uh, temperature difference between the measurement and reference junctions. So the issue about thermocouple is that the output is relatively low in the range of millivolt. As you can see here at the table, this is the output for uh, temperature difference. Uh, the output for every temperature difference, let's say in this example, between 0 to 250. So the output is low, so we need to do to have some what you call amplifiers, signal conditioning. So the suitable circuit for the signal conditioning is called as differential amplifier. If you go to page 32, okay, differential amplifier. So we have this amplifier. We have two input, V1 and V2. And so V1 is connected to R1, and then the other terminal of R1 is connected to the inverting input of the op amp, and then the inverting op amp is connected to R2 and then to the output, while V2 is connected to R1 and then connected to the non-inverting input of the op amp, and then we have R2 also to the positive non-inverting input of the op amp to the ground. So according to this differential amplifier signal conditioning circuit, the relationship of the output is equivalent to R2 over R1 multiplied with V2 minus V1. So we can so similar like this question, we can get um, the value according to the question. Okay, go back to this question. What is the suitable value of R1 and R2 to produce 5 volt output at the temperature 110? So if we can answer that directly if you capture or already comprehend the equation, and then you can you know be very confident you know that, okay, this is differential amplifier V out equivalent to R2 over R1 multiplied with R2 V2 minus V1. So if the input is 5 volt and then the output at 110 degrees Celsius is 4, okay, 110 degrees Celsius is 4.70 millivolt, which we have done that last week before. So we can find or we can determine the suitable value of R2 and R1. But what we're going to do today is to uh, derive the out equivalent to R2 over R1 multiplied with V2 minus V1. So the first thing that uh, you need to know is the ideal characteristic of op-amp. Okay, ideal characteristic of op-amp. The first thing is that the potential at the non-inverting input of the op-amp, or V, or we call as V minus, and then also we look at the potential at the non-inverting input of the op-amp, V plus. So V plus minus V negative equivalent to 0, or V plus equivalent to V negative. Right. Then next, for ideal op-amp, so very high input impedance. Infinity means that very high input impedance, so that the current that the current that flow into the non-inverting, I minus, is equivalent to 0 ampere, and also the current that flow into the non-inverting input of the op-amp, I plus, I plus is equivalent to 0 ampere. Right. So those are the ideal op-amp condition. So next, we do some derivation. So we start at node B minus. So we apply Kirchhoff current. So let's say this is I1. Let's say this is I2. So we apply Kirchhoff at node V minus. So we know that I1 equivalent to I2 plus I minus. Right. And we know that from ideal op-amp characteristic, we know that I minus is 0. So this is 0. So I1 equivalent to I2. Then using Ohm's law, okay, potential difference. So Ohm's law, V1 for I1, V1 minus V negative over R1. For I1, we apply Ohm's law, and I2 is V negative minus V out. Okay, in this case, V out over R2. Good, so then we get that our first equation. Now, for at node V positive, can say this is assume that I3 I4 to I3. Okay, apply Kirchhoff current at node V plus I3 plus I4 equivalent to I positive. So we know that the ideal characteristic of op-amp I plus is equivalent to 0 amp. So this is 0. Therefore, I3 equivalent to negative I4. Then we apply Ohm's law. So I3 is V2 minus V plus over R1 equivalent to negative 0 minus V plus over R2. So we rearrange this, we get that V plus is equivalent to V2 multiply with R2 over R1 plus R2. So if you can do the rearrange yourself, okay, you can get this equation as second equation. Now the next thing is that, okay, we we can okay, 2 into 1. We okay, observe this part. Okay, my equation 2 into 1. Okay, we know that okay, V plus is equivalent to V negative, so we can, so V plus here, V plus is equivalent to V negative. So therefore, we can okay, insert equation 2 into 1. We get V1 minus V2 R2 over R1 plus R2 over R1 equivalent to V2 R2 over R1 plus R2 minus V out over R2. Okay. So here we get so this is we can say that this is our third equation. Okay. So we use our third equation here as our, now we use that as our primary equation. Okay, equation 3 here. So from equation from 3, if V1, if V1 here is 0, okay, we do some assumption. So V1 is 0. So if V1 is 0, so we get 0 minus V2 R2 over R1 plus R2 over R1 equivalent to V2 R2 over R1 plus R2 over R2 minus, so we put this V out when V1 is equivalent to 0. Okay. So if we rearrange this, okay, this to be like this, negative R2 over R1 multiply with V2 over R1 plus R2 equivalent to V2 R2 over R1 plus R2 minus V out V when V1 equivalent to 0. Okay. Then so you can rearrange this, okay, back like this, V out V1 equivalent to when V1 is equivalent to 0 will be equivalent to V2 R2 over R1 plus R2 1 plus R2 over R1, then V2 R2 over R1 plus R2 R1 plus R2 over R1, that cancel, and we get V2 R2 over R1. Okay, so when V1 is 0, V out is equivalent to V2 R2 over R1. Okay, so that's one condition. Then you repeat the process using equation 3 here, but we repeat that for when V2 is equivalent to 0. Let me cancel all this. So if V2 is equivalent to 0, we use the equation 3 here. So if V2 is equivalent to 0, therefore V1 minus 0 multiply with R2 over R1 plus R2 over R1 equivalent to 0 multiply R2 over R1 plus R2 minus V out given V2 equivalent to 0 over R2. So this will zero out. Okay, then we can rearrange V out when V2 equivalent to 0 is equivalent to negative V1 multiply with R2 over R1. So when this is 1, so when V2 is 0, so V out V2 equivalent to 0 is equivalent to negative V1 multiply with R2 over R1. So so when we obtain the third equation, so when we have obtained the third equation, and then we have applied the condition when V1 equivalent to 0 and when V2 equivalent to 0, that is actually we are applying superposition theorem, which means that the final output of the V out is equivalent to the sum of V out when V1 equivalent to 0 and V out when V2 equivalent to 0. So therefore V out in this process is equivalent to V out V1 equivalent to 0 plus V out V2 equivalent to 0. Therefore, we know that V1 when equivalent to 0 is V2 multiplied with R2 over R1 minus V1 R2 over R1. So our V out is equivalent to R2 over R1 multiplied with V2 minus V1. So that's how we get this equation. Okay, so not this one. Okay, so we get that the answer there. Okay, so V2 minus V1. Okay. So we know that this coming back to here, what is the suitable value of R2 and R1 when the input is 5 volt, and then what is R2 over R1? 4.750 millivolt. So what we can do, we just choose, let's say R1 to 10 kilo ohm, fixed value. Okay, let choose this value, choose this value, and then R2 is equivalent to uh, so R2 is equivalent to 5 over 4.7 millivolt times 10k. Um, 5 times 10 divided by 4.7. So if R1 is 10k, therefore R is about 10.6 for ohm. But we cannot get standard value 10.64, so choose R2 equivalent 10 ohm. Okay, so that's the value, okay, that we can get. Okay, okay, next, what's in the question? What is the maximum temperature for an output voltage at the saturated value if arrangement as 1? So saturated value is basically when we look at the supply. So VCC is 20 volt. According to this, saturated voltage is 20 volt. Okay, VCC positive VCC is 20 volts. So what is, okay, the question is the maximum temperature output voltage at the saturated value, maximum temperature. So means that the output, okay, the maximum output possible is basically less V out. It must be usually must be then maximum must be less than 20 volt. But we can assume that, let's say maximum, let's say close to 20 volt. Okay, what what is the um, uh, temperature? So according to this, okay, according to this equation, the gain R2 over R1 is 10, sorry, that's can R2 cannot be small, right? Sorry, So if R1 is 10K, choose this value. My bad. This is wrong here. So R2 is equivalent to 5 multiplied with R1 over 4.7 millivolt. So multiply with 10K. Is it? Sorry, R2 is not 10. R2 is supposed to be 10.638 tens to the power of 6. Means to the power of 6 ohm. Or we can choose 10 mega ohm. Yeah, 10 mega ohm. So sorry, my bad. So if we choose R1 to 10 kilo ohm, so means that R2 must be 10 mega ohm. That means the gain R2 over R1 is 10 mega divided by 10K is around 1000 gain value. So if the V out maximum is 20, so V out is 20, so the gain is 100. So V2 minus V1 will be 20 divided by 1000, about 20 millivolt. Okay, V2 minus V1, which is the here, and the potential here will be 20 millivolt. So if we can find 20 millivolt, the value in the table, I don't think we can use this table because it is already out of the range. 20 millivolt. We cannot use the table, so we need the extension of this table. But never mind. So we just skip that part. Skip that part. And then number 4, using information from 1, 2, 3, 1, plot the graph voltage output for signal conditioning versus temperature range 0 degree to 400 degree. So again, to find the temperature range of 0 to 400 degrees Celsius, we need an extension of this table, but we don't have that here. So we're just gonna skip that part. Right. So we done that part of the solution of the uh, thermocouple circuit, and we proceed with what is data acquisition. And basically, data acquisition, DAQ. So you have basically done the uh, experiment. So that experiment actually involve data acquisition. So you are actually collecting data from physical data, which is more in the second lab, which is collecting the intensity of light and then convert into electrical signal. And then that conversion goes to your Arduino, and then Arduino convert the information into character. Then the character is sent, okay, through the USB. Then you can see in the serial port monitor of the Arduino. And also we have done using the lab view, where you can manipulate or you can replot the data into graph. So DAQ is basically a more specific system, okay, that we can use to collect and measure physical data. And this include the application of sensor, application of hardware like ADC. So you can see that your application before is actually a part of the AQ. But and also we involve software. You remember software what we have used software last time, using Arduino IDE or let view, so to visualize the data and use. But to be more in technical detail, data acquisition has is more dedicated for industrial and scientific applications. So all these, okay, all this we have seen in practical. The component, okay, remember the last time what kind of the sensor that you use, light dependent resistor, and what is the signal conditioning of the light the depending the resistor. Basically you have a VCC and then R and LDR, your LDR, and your output, which is a simple voltage divider, where okay, the output is equivalent to the RLDR divided by the fixed resistor plus RLDR multiplied with VCC. So your output is basically proportional to the resistance value, the resistance value of the LDR over the uh, ratio of the resistance over the fixed resistor. So and then your output go to the Arduino, and the Arduino has the analog input, which is the ADC, the analog to digital converter, which you have covered how the conversion, the governing equation in the previous chapters. And then the data is furtherly processed or transferred you can transfer into other machine or device. So in our case, we transfer that information to our laptop, okay, using USB, and then we use software, okay, okay, to let you basically to see the information. So this is just looking back uh, in more technical term, what is data acquisition, but actually you have done it. You have do it in the lab. So you have hands-on. Suppose you're supposed to have hands-on experience on the data acquisition. But what we have used is basically uh, simple. We can say simple or low-end application. But in the industry, there are high-end data acquisition with higher capability or higher capacity, which we will discuss later. Then also we have another type, a type of data acquisition device, which called as logger. So it works the same, or the purpose same like data acquisition, but uh, in terms of the data we transmit into our device, but the data for data logger, the data is recorded either on the device itself, or transmit into the network, or any kind of network like GPS or wireless and so on. So you can go in detail later, but this is the big comparison between the data logger and DAQ. Like for example, the sampling rate. Sampling rate means that how fast, okay, the data can be sampled. Okay, so this is very important when you know that the data you collect has a variation in frequency. The frequency, or the frequency matter. If frequency matter, then you need to know, or you need to choose the proper sampling rate. So your signal, the according to the rules, okay, the sampling frequency must be at least 2 times higher than the signal frequency. Sampling frequency must be at least two times higher than the frequency of the signal. For data logger, so the sampling rate or sampling frequency is in the low and medium, but for DAQ can go up to very high, the range of megahertz and up to gigahertz, or sometimes okay go in byte per second. Okay. So, and then if you look other than the specification, like data logger have a smaller, usually have a smaller number of input. Okay. So for data logger, the capability is okay to record the data for a very long period of time. Even in some application, data logger record data up to years. Okay, but the EQ system, uh, it means that does not store a lot of memories or a lot of data. Most of the data will be transmit or displayed for data acquisition, or uh, it will not, the data, if it will not record in on the AQ itself, itu bila transfer into another device like your laptop and your PC. Okay, so the other things that matter is like the for data logger can be used for real time, but sometimes not available. But for the AQ, used for real time application. For data logger, it has independent, a separate power supply. Okay, because for data logger, usually you use it at in remote places. For DAQ, we use external, and then the DAQ cost is lower than the DAQ system. Some factors when you consider to choose for data acquisition is these are the factors. You can say the accuracy, which is related to resolution. So the the resolution smaller better, smaller resolution means that it give better quality of the signal. And then channel, okay, commonly if the AQ comes into the multiple of 16, 32, 64, 1024. So in that uh, number lah. And then whether you want to record analog or digital system, or you want to record sampling rate, and also what are the conditioning requirement, like before um, we look at the thermocouple, where it require differential input amplification, and then cost is the last thing that comes. So cost. So if you have unlimited cost, you can get the best. Otherwise, you have to trade off with uh, system that can barely or fulfill your requirement. Right. So this part, visual instrumentation, so I can say that you have do some exercise on it. In particular, which is using the lab view. So lab view is one of the visual instrumentation which can help you to analyze and display your output into graph, for example, and also you can do the control, okay, your signal or either stop or. But our practice so far, we just communicate or open the channel for on the Arduino, and then we read the information. We haven't done anything backward. I mean, give feedback from our alert view or our instrumentation, visual instrumentation to our device. So that maybe later lah. So like lab view is a powerful tools. You have seen that how to construct the lab view in the lab, where it has the front panel, and then it also have the uh, workspace where you can connect the component, and each component or function uh, can show you or help you to communicate with your hardware or device. Right. So other software than LabVIEW, it's like MATLAB or Agilent. They are also have the capability for visual instrumentation. But in my opinion, LabVIEW is much more powerful uh, in terms of visual instrumentation. For MATLAB, it's more powerful to do analysis, simulation, and Agilent is more. They are keen on, or the strength of Agilent is more to what I've seen is more to uh, device like device to hardware. Okay, so we take a 5 minute rest. Okay, we continue for virtual instrumentation. Okay, and then next we're going to it's going to be the last part, some of the last part of our um, content. We look into the different type of communication protocol or the communication type between devices in data data management or communication protocols. So there are two basically communication types of protocol: inter-system protocol or intra-system protocol. So inter protocol system is basically used for communication between different system. Two different system, completely two different system. Like for example, okay, CPU in our laptop, okay, communicate with our microcontroller. So we actually did that in our experiment, which is communicating our laptop with our microcontroller, which is Arduino, using USB port. So this allow to um, communicate data or exchange between various devices and system. So there are okay, different type or category of uh, inter protocol system. You can see USB and UART. Okay, so we UART basically universal asynchronous transmitter and receiver, and UART have its variation called as universal synchronous and asynchronous transmitter receiver USART. So the difference between UART and USART is that the USART, okay, have a clock and also that and then another capability include for USART is transmitting data without clock. That's the difference. Which means that USART only submit or transmit data without clock synchronization. Okay, but for USART or synchronous mode, it has clock. And then another type of uh, inter connection is called as USB protocol or USB. Now let's see at the UART. Okay, UART universal asynchronous transmitter receiver. Basically, this communication between two different devices, okay, on the data bus. It is a serial communication protocol, means that it sends data on the single line. Okay, so for U the UART has a half duplex, means that it only can send data and then change the mode into receiver in the next cycle. So it cannot, for UART, it cannot read and talk at the same time. So that half duplex. But for USART, so it has two quiet protocol, means that for both uh, for the, let's say we have two device, the first device and the second device. So the first device also can communicate or send data to the second device, and in the same time, the first device can receive data from the second device. So that also uh, for the second device also can, okay, read and listen at the same time. Uh, then USB protocol. USB protocol is asynchronous. Asynchronous means it has no clock. The data is transmit uh, according using the protocol bit by bit. So it has four wires: red, white, green, and black. If you can strip off the USB cable, and the transfer speed is about up to 400 megabit per second. All this can be converted into baud rate. If you remember, in our previous class, previous lab, we use application at 9600 baud rate. Baud rate. So that is actually can be converted into uh, byte per second or bit per second, the baud rate. But the cable is limited to 4 meters. Cannot stretch uh, because of the signal or that is used is low voltage or 5 volts. Or then we have intra. So intra is the protocol for communication within the same system. Okay, the same device, a device that can talk to other device, or device, not different system, device. So inter is system within different system. For intra is device to device. Okay, like for example, in this example, in this slide, microcontroller, let's say our Arduino is communicating with the a module. Okay, this module is ADI S16233, is digital three-axial vibration sensor. But if you remember that we also have, okay, can communicate with our Arduino with LDR module, and our LDR module has digital and also analog. It can you can communicate with the microcontroller with digital and analog, but digital analog is more to uh, connecting to the ADC, but for digital, the data or is convert into digital signal and transfer into the microcontroller. So these are the popular uh, types of intra-system protocol called as I2C, SPI, and CAN. So when you, I think most of you are now already involved in this application where you communicate with your Arduino and like for example motor driver circuits, okay, and so on. So I2C, okay, can same device, a similar device. I mean a similar device like Arduino with Arduino. So not two totally different system. So same type. Okay, same type. Not for in. So this is inter. So it is can communicating with the same type of device, which is Arduino and the Arduino, and it is this called as I2C, integrated circuit protocol. Um, and also another one we call as SPI. This serial communication developed by Motorola. So it's much more complicated in terms of the wiring for SPI. So it can so like you can imagine many Arduino connected to a master. Uh, then the master coordinate the communication between the slave, okay, and the master. So means that the master, okay, can determine which device talk and the other device listen, or vice versa. So in the full duplex means that the data can be sent and received at the same time. And also this is another one called as CAN protocol, controller area network. CAN protocol based on network oriented transmission control. So these are the comparisons in terms of the connection. First, we go into the communication type. For I2C is half duplex, and also CAN is half duplex. But SPI is full duplex to transmit and receive at the same time. But this is only transmit or receive the data, transmit or receive, cannot at the same time. So if you look at the speed, SPI has the high, uh, but for many master, which the I2C can support, and also can can support, but SPI cannot support multi master. Data integrity check for I2C and SPI, no. Data integrity means that there is no, in the protocol, there is no way how to check the validity of the signal that transmitted. But can CAN have a way or have a protocol how to check the data integrity? In terms of the uh, application, like I2C is for low speed application, for SPI for high speed communication, but and CAN is more to automotive or industrial automation. Right. Now that's we have covered about more to the previous example is more to um, the communication for small the intra and inter. But now we're going to look at industrial instrumentation protocol. Means this is more high end application, or more to system that is more complex and much wider and more device. So the first one is called as RS232. So RS232 uh, is asynchronous. Asynchronous means that no clock coordination. The data is transferred asynchronous, bit by bit. Uh, so it only have internal timer. Okay, so there is no coordination. No, there is no dedicated clock to coordinate the data transfer, and it used binary system, and then the data in ASCII format or the ASCII character. A character. So you actually, what we did last time. Okay, we are transferring our data from our Arduino, okay, to our laptop using the ASCII format. So that's why when you want to, okay, plot your data in the lab view, you cannot directly, okay, connect the data output to chart, but you have to do some conversion, which is converting the character into double or float value. So I strongly believe that if you do, put your heart last time in the lab and then experiment, you follow my instruction, you can appreciate what I'm talking now. So that's why very important you focus, okay, focus on the lab last time. So the RS-232, I can give you example a device like barcode reader, and this port, uh, it if you look at the old PC, they have the female port of the RS-232, but it's already depreciated or have been replaced with USB. So it's still being applied in the like in the for devices in retail, for example, like a barcode scanner, and but usually they have that RS-232 to USB converter if you want to connect this device into to the modern or the latest device or the latest laptop like nowadays. RS-4456 is the upgrade version of RS-232. Okay, it's the upgrade version. Uh, but same number of pin, 1, 2, 3, 4, 5, 6, 9. Okay, but the in term of the protocol is different. Um, this used for communicate with multiple device at the same time. For RS-232, it's one-to-one device, one-to-one device. But RS-486 for multiple device. Multiple so means that at the same connection there will be uh, uh, many could be many devices that connected in the same line. So it can go up to 32 devices in the same line, or we can say at the same bus, and then the distance can go up to 1,200 meters. Next, we have Ethernet or wired communication control, Ethernet. So the protocol is defined under IEEE. So if you are into IT, so in this communication use network or internet protocol for routing. This connection can go few kilometer, and then the speed can go up to 1,000 megabit per second. Then we have highway addressable remote transducer protocol or HART. Okay, HART is a master-slave protocol. It can be used in many modes like point-to-point or multi-rep of communication for smart field instruments and central control monitoring system. Then the other thing is that it can be used, usually used to 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 communicate or connect with instrumentation device. Okay, instrumentation device. Then we have this other modes like mode bus RTU. Okay, thing you can read and a mode bus RTU in more details. Profibus and Profinet and Interbus. So just I give you the summary. The summary for the all the system that is given in especially for Modbus, Profibus, Profinet, and Interbus. So you can here is list out the description. For example, Modbus. This is communicating used to connect industrial electronic device. For Profibus, communicating standard for automation or in more detail in automation. Profinet is designed for collecting data from and controlling equipment, and Interbus serial bus used for communicating between industry control and system. So these are the physical mean that the connection or the protocol, like Modbus that's is used serial, but okay, RS232 and RS486 protocol. For Profibus, you can use RS486 or fiber. Okay, Profinet, as the name suggests, it is using internet. Interbus using serial or fiber. So for the rest, okay, like Modbus, Profibus, Profinet, and Interbus, this is more to like industrial automation or system automation, uh, include SCADA. So these are the advantage and disadvantages of the systems. Like for example, RS232 is simple connection, one uh, one device to one device. But the advantages is that limited number, limited cable length, and then can easily interrupted by noise and interference. But if you want to upgrade that connections, you can use RS486, where it can use longer cable and more complex. And for internet, it's a high data transfer rate and widely used in LAN and WAN environment. But the advantages is higher in cost and require network infrastructure. And for the rest, okay, like hard Modbus, Profibus, Profinet, and Interbus here, you can okay, already share that this advantage and disadvantages. And then you can in in the in summary for like Modbus, Profibus, Profinet, and Interbus. So they are more to automation. So automation. So the disadvantage is that it does not easily available for end user uh, like individuals. They usually it is more accessible to industry and also with people with more um, what you call um, budget or funding. Right. So if we go to this exercise, I think we will go give you the answer later. So next, what's next? Happen next is that uh, I want to I'm going to set up the submission page for your second lab, and then I will give you until the 1st of July. Okay, 1st of July, the due date. Okay, I will announce that in the group to submit your report for the second lab, because we have already done that exercise. I think the last 2 or 3 weeks. You have supposed to done the report as well for the second experiment. Then so I think we going to spend one last class face to face this Thursday. We will try to cover up some examples from the previous questions, and also I will share the previous finals and answer in the group. Also will declare. I just got it from the coordinator. So I think you can use the sample of 5 questions to study, right? So so that's I think that's all for today. Let's conclude our lecture for the syllabus. We spend some time for our last lecture session this Thursday, and to discuss some of final exam question. Okay. Thank you very much, everyone. To see you this Thursday.